Okay, so today I hope that we finish up until this lecture, but if not, I'll do my best to finish here, like after naive Bayes. Because actually, naive Bayes is like a generalized version of that too. So, on the other words, LDA and QDA are like special case of naive Bayes. Yeah, and naive Bayes and the Bayesian decision theory are pretty much the same thing. Okay, actually, before first, let me recap a little bit. All of these are generative classifiers, and they are parametric methods. When we say they are parametric methods, mean that they actually have a lot of assumptions about our data, right? And you may find that in future, the linear LDA and quadratic LDA will pretty much, actually, especially this one, the linear discriminative analysis or LDA, it looks very similar, this one is very similar to the linear regression. Very similar at the end. And QDA would be very, very similar to the polynomial regression, which we haven't learned, but that's okay. But if we remember from our last lecture about neural network, actually linear regression and polynomial regression whatsoever, they can all be kind of structured with neural network. So if we talk about, whether or not they are parametric, non-parametric, maybe we can put it like on a bar where you have non-parametric on the leftist and parametric on the rightist. LDA and QDA is like highly parametric because it has a lot of assumption about your data. They have like an assumption about the distribution and then the assumption about your function. Meanwhile, the linear and polynomial regression may be somewhere around here. And then you have like a line where you say that, okay, if you cross this line, then it's no longer what we call parametric. It will then become non-parametric, which is like a neural network. Actually, the difference between polynomial and linear regression versus neural networks, they are just like, the neural network is the concatenation of linear layers, which is like if you use linear function after linear function after linear function, then you can actually cast that as neural network. So that means that it is like the only thing that define, whether or not they are non-parametric or parametric is just like a exponential term on the model weights. Like the neural network probably be like a polynomial, like a function of polynomial weights compared to the linear model. It's just that operation. Meanwhile, if you talk about LDA, QDA, there were definite assumptions about your data distribution. And also the naive Bayes will be somewhere around here because naive Bayes generalized version of LDA and QDA is like a version where you pretty much just formulate your equation. You haven't yet put in the assumption of what distribution that has to be, but you can define what that could be. It's like in between, but there are certainly relying on assumption of data distribution. Yep, so that's how strict they are. Yep. For linear model, we do have a little bit of the assumption of the data distribution actually. If we think about what we've done previously where we have like using hat matrix, stuff like that, we have to normalize the feature, make sure that the noise is zero, something like that. The noise is zero means something like that in order to derive all those properties. So that's kind of like the reason why it's still categorized as parametric model. But if you use neural network, you don't need to normalize your inputs. You can just feed them in, and it will learn everything based on like the how your data is driven, your model to learn the parameters. So that's the high difference, like the main difference between these guys versus this guy. Sorry, this versus that. Okay. So what are they? Actually, all these methods that we would learn today, they are the methods based on what we call Bayesian decision theory. So it's actually based on how we derive the Bayesian relationship. And then, as we can guess from the name, from the Bayesian, then that become like a boundary decision. And after that, maybe we put some special types to it, then it become LDA and QDA. Yeah. So that's the overall. Okay, first of all, I believe that we all kind of familiar with this equation. Let's say we used to call this likelihood in our previous lecture, because usually when we learn for beta or maybe model parameters, those parameters usually tied with x, right? So we usually call it likelihood. But in this case, when we want to estimate for the class, then what becomes the unknowns is the class label. Then this become like a posterior in this setting. But please don't worry, I will not try to change the name. We will just call it probability of being in a class given x. Just that, okay, to make it simple. And with this probability, if we use Bayes rules, we can come up with this relationship. And actually, this is where the terminology of being generative come from. So when we say it's a generative model, usually it refers to the fact that we will use this probability to drive how we will learn the model parameters. Because if you think about the model parameters, it actually will be the one that is associated with x. And as I mentioned before, if anything related to x, a probability of x, then that is generative model. But this is like, because yes, we will use probability of x given y to be the one that is driving this boundary method. Then the model parameters that we will learn are going to be the model parameters associated with probability of x given y. So that's kind of the reason why we call it generative classifier. It's mainly because of the usage of this probability. So just to recap, in our previous lecture, we probably not call this likelihood, but call this like a posterior. And this one is likelihood. But in this lecture, maybe in the slide, it will call like on the opposite way, because the unknown is shift to be this one. But in fact, whenever we classify it as generative or discriminative, we still look at our old terminology, that is this one. Okay. Okay, first of all, if we look at this method as a Bayes decision boundary and how it classifies a sample, let's say given a sample, we can write the probability of that sample being in class, maybe class 1 or class 2, using this Bayes relationship which we have just seen before. But how do we use this probability to judge? It depends on the probability of being in one class that is higher than the others. So on the other word, let's say if you have this relationship that, okay, we want to judge if x belongs to class 1 or class 2, that means we have to compute prob of y being class 1 given x, and compute that and compare that with probability of y being class 2 given x. Let's say if there are only 2 classes. But if there are more than just 2 classes, that means if we have class 3, then yes, we have to do like prop of y being in class 3 given x, and you find what is the highest. So that's how you classify x, right? So when we use this value of probability, one way we may compare on the probability just like this. Or we could take the logarithm, and then compare it. So in this case, if you take the logarithm on your first term that is on the left, you would get this one that is according to whatever we get at the top. And we ignore this denominator. And the reason is because if we think about that we receive, let's say, a probability of our input features, that input features will be the same whether or not you are classifying for class 1 or class 2. So that's why you can remove it. Or on the other word, if you write it fully, it will be equivalent to writing this term at the end of that term. Right, and then you compare these two, like this on the left and this on the right. And what you would get is that actually that two terms will negate each other out. So you don't need to think about this one. All you have to think about is the top one. But what does the top one actually signify? So we look at the originality of that, the denominator. Probability of y being in class maybe 1 or 2 or 3 is pretty much like, we can say in this way, if chance that y belong to class 1 and class 2 are about the same, then probably you have like unbiased class, right? So like prop of y equal to 1 equal to prop of y equal to 2, and that means that's no bias. But if you have the probability of being in class 1 higher than being in class 2, then there are some kind of bias. It's like some kind of weight that you have in here. So that is the bias towards being in a certain class. But what could also driven this, even though you know that the class are unbiased, that means that if probability of being in class 1 is the same as probability of being in class 2, what would drive the differences is the probability between x and y. That is the conditional probability between, let's say, probability of x that y being in class 1 versus probability of x of y being in class 2. And this probability will be what we call the relationship between our input features and the class. And actually, this relationship will be the one that will mainly drive the decision of your classifier. So will be the main drive towards the class, or maybe like a main, it's like a main term that define whether or not it's going to be class 1 or class 2. Alternatively, you can think of the fact that, actually probability of y equal to 1 and 2 here is probably the same for every x, because it's something that is just there. But what is different for different input is this term, like this one. It could change for each and every x that you have. Yeah. And what does this look like graphically? Okay, here you only see like if value 1 is higher than 2 or maybe something like that is the value comparison. But if we provide a PDF plot, right, it could look something like this. Actually, this one, I kind of do it wrong. It should be prop of y equal to 1 given x and probability of y equal to 2 given x. And maybe in this first example is when you cannot really make a decision. And if you look at the area under the curve, actually the two area are about the same, right? But if one is larger than the others, okay, I'm sorry, that should be y equal to 1 given x and y equal to 2 given x. Yeah. But if one is larger than the others, that is just like this example, then you have a higher area under the curve compared to the other one. And if you consider like not just the area, but what if you extend it a little bit to something like maybe in spatial visualization, maybe if you could do like maybe x and y here, maybe if you could do that, you will see like a larger area belong to the second class than the first class. But of course, what you also see is that there are some kind of decision boundary that we'll be making depending on who takes more of the area. And if it was, let's say, an LDA algorithm, usually this decision will look more like a straight line. Meanwhile, if it was a QDA, okay, if it was LDA, usually it would look like a straight line. But if it was QDA, then that would be like a curvy line between the two. It's like the curvy boundary from the top view if you look from the top between x and y. Yeah, but we will come to that example. So before we go into detail of what LDA and QDA, maybe let me introduce you the first thing that was, what would this look like in the naive Bayes? Because naive Bayes is like a generalized version of that too. So in naive Bayes, what you would do is that you would be considering different like configuration for the probability of x given y for naive Bayes. It could either be something like a Gaussian. Sorry, that's what I taught in the morning. Let's say if probability of x given y is a Gaussian, then you plug in this term as Gaussian, and we'll call it Gaussian naive Bayes. But what if we replace it with something like a Bernoulli distribution, then it becomes like a Bernoulli naive Bayes. So yes, naive Bayes is just this. It's like you replace that probability of x given y to some function, then you get that new posterior probability, or maybe we could call it a likelihood in the other lecture. Yeah, that's probably like the core idea of naive Bayes. But the thing is, if we look at this naive Bayes method or maybe approach, what we see is that, okay, if we plug in maybe prob of x given y as a Gaussian, usually what we have to keep in mind, okay, let's say if it's a Gaussian, what we should keep in mind is that we know it's the probability of x given y, but if we write it this way, actually this way of my writing is not precise because, well, x is something that's given, is an input. But what make it a condition on the label y usually being the parameters mu or sigma here. On the other word, sometimes we would rather use the notation where xj given y, j equal to c, let's say, being the probability that is conditioned on the maybe the means and variance that's associated with that class. So sometimes they would change from sigma to sigma c so that it can like take some conditioning on that class label. Sometimes it actually more precisely I should use that notation like with subscript C. But what if we change this probability of x given y into like a Bernoulli distribution, right? In a similar way, then that will be like a Bernoulli distribution where the probability of belonging of x taking an even q will condition on the value of y equal to c. And let's say if you have a relationship between x and y that kind of look like table like this. Let's say if y value is 0 and 1 and x maybe minus 1 and 1, and this will be like a q event, like q could be minus 1 and 1, and you can have some probability like maybe this one is 0.8, this is 0.2, this may be 0.4, 0.6. Then probability of x being let's say probability of q equal to minus 1 given y equal to 0 will be 0.8. Yep, so for Bernoulli distribution is kind of like an instant of the event of x. Something like that. Yeah. So yes, if you have Bernoulli distribution, you can model situation like this. But what I would like to point out a little bit, that if we plug in the value of this formulation of x given y into this distribution, then you get something like this, right? Because the first term belong to prop of x given y and the last term belong of prop of y being in the class. Then you take the logarithm. Then what you get, then what you get will be like a x, like a kind of like a function of x here plus log of prop of y equal to c. And so for the first term, you get something like a linear function in x. And the second term is just a log of y equal to c. So you have some kind of linear function there. And actually, if we think about what's inside here, it is like, what's inside here is like, if we give this probability like a value, let's say maybe xj times a plus 1 minus xj times b plus the last term, that one. That means that we can learn from a and b, just like when we do the linear regression. We have a linear function of x with the model parameters a and b. We can learn for these a and b with our training samples, right? So that means that whatever here, we can see that it's actually taking a similar form to what we've done before in the linear regression. But what about LDA and QDA? Actually, previously, when we talk about naive Bayes, please be careful for one thing. Naive Bayes, you can replace this probability of x given y for many, many distributions. Let me search for it. You will see like, yep, naive Bayes. I think I showed this in the morning. Yep, you can have Bernoulli naive Bayes, that is our example. You can have multinomial with naive Bayes. And you can also have like a Gaussian naive Bayes, and there are more. So there are many, many distributions that you may want to consider, but that also depends on your situation, like what you think your data x is going to be. If it's continuous value, probably Gaussian naive Bayes is one of the most suitable choice that you can make. Yeah. Okay, so that's it about this algorithm. But if we consider like LDA and QDA, there were additional assumptions to make, and therefore it will reshape this function into like linear function and quadratic function. And this one will have like a linear boundary. But this one you will have like quadratic boundary. But this one depends on your assumption of pop of x given y. Okay. And in the training phase, after we get all of these equations, we will learn them in the same way that we learn using like maybe MSE, mean square error. Yeah. So, okay. Let us take a look at this example. In this example, we are using pop of x given y being like Gaussian distribution. So in this example, we focus on just this term. And as you can see, let's say for an x, right, we have pop of x given that y equal to 1 or pop of x given that y equal to 2. Versus if you have another x and you compute the probability of x2 given y equal to 1 versus x2 given y equal to 2. Okay, I should use that way. And as you can see here, okay, for your first example, if you look at this graph, what it means is that if x belong to y1, and we know that, okay, let's say if we assume that for y being maybe class 1 or class 2, the chance is the same, then we can put this way. So that means the only thing that drives the difference is just this term between the two. And if we plot the histogram and we get this example, this means that the chance that x belong to class 1 is larger than class 2, as the area belong to this class is higher. On the other hand, if we look at the second example, and we get this probability, that means that x2 will likely to belong to class 2. But that also depends on, let's say, maybe the condition of x. Usually when they do this, usually this means the value of x. And if we do something like a scatter plot, right, and draw the curves. So, I think what it means in this graph is that if there were two-dimensional x, so x1 is one of the x here, like this one. Sorry. So yes, so that means that it's not two different samples. They are actually two different dimensions of the same samples. So if we were to put these two histograms on this spatial dimension, then we probably see something that if x1 is lower than 3, from here downwards, then this will, there will be the area of being in class 2. But if we look at this forward, depending on value x, then this will likely belong to, this one belong to class 1, and this one belong to class 2. So yeah, that was the red area here. But if we look at x2, x2 lower than 0 will likely to be in class 1. So yep, around this area. And higher than 0 likely to be in class 2. Yeah. And you can see that this actually have some kind of quadratic boundary. So Yeah, one way that we can separate them is to use some kind of quadratic boundary or QDA. But if we use LDA, probably our decision boundary would look something like that, like a straight line that divide between the two. Okay. So let's have like a 5-minute break and we'll come back to naive Bayes.